Hello everyone. This project is titled Control and Navigation of Differential Drive-Wheeled Mobile Robot. This project was conducted at the Robotics Innovations Lab, Center for Product Design and Manufacturing at the Indian Institute of Science. The project can be divided into 5 main parts, namely, the introduction of the project, followed by learning objectives of this project. Then we shall dive into the assembly of the mobile rover and the target object. Then we shall perform exercises to understand robotic concepts and see the results ourselves by experimenting on the mobile robot. Then there will discuss about the final conclusions of the project. Now let's start with the introduction. This project consists of a programmable mobile robot which communicates over Wi-Fi on MATLAB. For image processing tasks to be used for localization, a color-coded sticker shall be installed. The robot will be programmed to perform tasks like navigation, line following, and obstacle avoidance. The objective of this project is to assemble and configure robotic components with Arduino boards, and understanding the capabilities of Arduino MKR1000 and Arduino MKR Motor Carrier. Along with that, we shall also understand about robotic fundamentals and gain insights into the working of differential drive robots and simulate their behavior, control their speed or position, perform localization and navigation in an arena, and performing line following with obstacle avoidance. We shall use MATLAB for programming the mobile robot to perform these tasks. We shall use image processing algorithm for localizing the robot and getting the robot to navigate the arena based on the results from image processing algorithm. Now let's assemble the mobile robot and the target object. The components required for the mobile robot are as follows. The steps to assemble the mobile robot and the target object are as follows. Mount the forklift arms to the side piece. The lock nuts must be tightened without constraining the arm's movement with the help of pliers. Mount the caster wheel to the bottom piece and assemble it with the side piece. Make sure that the holes in the bottom piece are pointing toward the previously assembled pieces. Attach the DC motor to the top plate. Make sure the motor bracket is aligned at the center of the motor. Mount the MKR Motor Carrier to the top plate and connect the cables of the DC motors. Pay attention to the color and placement of the cables. Connect the MKR and the IMU shield to the MKR Motor Carrier. Mount the top plate to the left side piece. Screw the servo to the servo stand and attach it to the bottom piece. Mount the servo head to the servo arm, then attach them to the servo. Make sure that the servo angle is aligned with the forklift's movement range. Place the module head holder piece and connect the module cable. Mount the forklift front piece. Mount the forklift arms to the right side piece. The lock nuts must be tightened without constraining the arm's movement with the help of pliers. Attach the right side piece to the rover. Click mount the forks. Mount the shaft and shaft collars to the forklift arms. Connect the ultrasonic sensor. Put the rubber tires on the wheels and attach the wheels to the DC motors. If the wheel hub hole is too tight, slide the D shaft through several times. Insert the battery between the top and the bottom plates and plug it to the MKR motor carrier. Stick the vision recognition sticker on the disc and attach it to the rover. Make sure that the red circle is precisely pointing forwards. Now we shall assemble the target object. The rover and the object has been assembled. The isometric view of the robot and the target object are as shown. Next we shall perform exercises to under the concepts and perform experiments to validate our understanding. The following exercises are to be performed. Before performing the exercises, we have to set up the Arduino MKR1000 with MATLAB. First, we have to connect the MKR1000 to the system via micro USB cable. Then in the MATLAB control window, in order to set up the Arduino board, we shall use the command Arduino setup. After this command is executed, an Arduino setup window will appear. The next steps are as follows. First we shall select the how we want to connect the Arduino board, which in our case is Wi-Fi. To connect through Wi-Fi, enter network security details. Next we shall select the type of board, which in our case is MKR1000, and select the available port assigned to it. Then we shall select the required libraries to perform the exercises. As of now the libraries are I2C, SPI, Servo, Motor Carrier, Ultrasonic. To upload to the Arduino server, click on Program button and it will start uploading. This process takes some time. After successful operation, go to the next step to check the connection. If everything has been set up properly, it should show a successful connection. So we have set up our Arduino board with MATLAB over Wi-Fi. Now we shall go to performing the exercises. The first exercise we shall perform is to characterize a DC gear motor. We shall characterize the DC motor using PWM-based speed control. The principle of this method is as follows. We supply a fixed voltage, which in this case is the battery voltage. Due to this the motor starts rotating. Then the voltage is removed and the motor coasts. By continuing this voltage on-off cycle with a varying duty cycle, the motor speed can be controlled. This is not a linear operation, but with a few assumptions which are usually valid under motor conditions, the PWM can be approximated as being linear. The linear model of the PWM-based amplifier can be described as supply voltage times pulse duration equal to equivalent voltage seen by the motor times switching period. Now the equations guiding the operation of DC gear motor are as follows. We assume shunt motor operation. The voltage, the induced back EMF and the torque equation are as follows. The results obtained are as follows. From the equations guiding DC motor, we can see that the nature of shaft speed versus armature current is approximately linear and decreasing in nature. For shaft speed versus torque, it is linear and decreasing. For armature current versus torque, it is linearly increasing. Moving on to the next exercise, where we shall determine whether the DC motors and the servo motors are responding to the given commands in a physical environment. The MATLAB code for the same has been described as shown. After running the following script, we shall observe that the robot will move in a straight line for 3 seconds, followed by the servo going to an angle of approximately 90 degrees. After 2 seconds the forklift will be in maximum position, i.e. around 180 degrees. Moving on to the next exercise, where we will perform kinematic and dynamic modeling of the mobile robot and simulate the robot's motion. We shall start by understanding the kinematics of the mobile robot. The parameters of the mobile robot are as follows. A radius of rotation r, rate of rotation or angular velocity omega, instantaneous center of curvature, forward velocity v, wheel velocities vl and vr, and robot length l. Let us start by kinematic modeling of the differential drive robot. Rate of rotation or angular velocity can be defined as the difference of the right and left wheel velocities divided by the robot's length l. The forward velocity can be defined as the half of the sum of the two wheel velocities. Wheel velocities based on wheel radius and rotational speeds can be defined as. Plugging these values into the previous equations yield. Arranging these equations and solving for rate of rotation of left and right wheel can be written as. In matrix form, it can be shown as. The dynamic modeling of the differential drive robot can be expressed as a function of driving motor torques and linear and angular velocities derived from kinematic modeling as shown. Proper citation has been cited. The block diagram for the open-loop control of the mobile robot has been shown. The forward and angular velocities are inputs to the system. Then these variables are converted to wheel velocities, which drives the robot. Using the kinematic equations, we shall now drive the mobile robot using open-loop control. We give forward velocity of 6 cm per second for 5 seconds and an angular velocity of 36 degrees per second for the next 5 seconds, as shown as input commands. The results are as shown. As we can see that under open-loop control the robot has neither traveled the desired distance nor its final orientation is desirable. The percentage errors for both the cases are as shown, which are closer to around 100%. The results obtained from the open-loop control are quite unsatisfactory. Possible reasons for failure may arise from the communication lag over Wi-Fi as well as the lack of feedback. To overcome the limitations of the open-loop control, we shall use a closed-loop controller. Closed-loop controller has open-loop system in its forward path but has one or more feedback paths between its output and input. The closed-loop controller used is the PID controller. The PID controller is a basic but powerful controller. It consists of three terms, namely the proportional, integral, and derivative terms as shown by the equation. By varying the values of these terms, an optimum desired results can be obtained. We shall apply the PID controller to control the distance traveled and the orientation of the robot. The block diagram for the closed-loop control has been presented. A feedback has been provided for controlling both the distance traveled and the orientation of the robot. The results obtained has been shown. After trial and error method, the PID constants Kp, Ki and Kd for distance traveled and orientation has been shown along with their final percentage errors. Performance comparison for both the open-loop and closed-loop controller has been shown. As we can see that for both the cases the final percentage error for open-loop control is significantly higher. When working with mobile robots, it's often important to know their location as they move around. This exercise will show us how to use a webcam to localize the robot's location and heading. To ensure that the robot remains in the webcam's field of view, the robot's movement will be constrained within a designated arena. We will start by building an arena and then perform some calibration steps to account for conditions specific to our setup. We shall start by building an arena for the robot. The following image shows an example arena for the robot by using a whiteboard and black markers. It can also be built by using some white paper and a black marker. The main requirement for your arena is that it must have a white background. The size of the arena is flexible, but it must fit within the field of view of our webcam. Also ensure that the webcam be placed at least 100 centimeters above the arena to get desired results when we localize the robot and the object. Next, we shall calibrate the arena and the environment for the image processing algorithm. For the calibration to work, it is important that it should know the dimensions of the arena. Units should be in centimeters. Then we shall initialize the webcam and calculate the transformation that gives us the orthogonal view. A question may arise that why we are computing the orthogonal view. It is because typically, it is hard to place the webcam directly over the arena, and instead the camera is placed where it takes images from some downward angle. Image processing can be used to translate the image to a corrected version of itself, which will make it easier for us to localize and calculate the position. The webcam image is displayed. To compute the transformation of the image, click the four corners of the arena in the image. Ensure that the robot is in the arena. As the webcam takes pictures from an angle, the robot's height is altered differently for various distances. To account for that, we shall calculate location offsets for the robot and the object. For this, we place the robot on the edge center of top, down left and right edge centers. Then we have to calibrate the location offset of the robot by setting the position of center of the disk and center of the robot, where it has been placed. Similarly, we have to do for the target object. Finally, we will calibrate the color threshold of the disk to account for the lighting. On the image that appears, ensure that you select the circles in this order: red first, green next, and then blue. With that, we have now calibrated the parameters to get an orthogonal view of the robot, corrected for any location offsets within that view and accounted for how lighting can affect the RGB values for colors. All the calibration data is saved and will be reused during the execution for localization of the robot and the object. Now that you've completed the calibration, Let's see how to calculate the position and heading of the robot within the arena. First we must prepare the MATLAB workspace. For that we clear all existing variables and load the calibration data we saved in the previous step. Here we load 4 data files, namely color.mat, which consists data related to the color threshold of the disk. Then we have ortho-calibration data.mat, which consists data related to the corners of the arena, center points of the edges, and finally we have the data for the location offset for the mobile robot and the object. Next we shall calculate conversion factor depending upon the dimension of the arena. The conversion factor will be calculated on the same dimensions used while performing calibration step. The conversion factor calculated relates the real-world dimensions of the arena in centimeters to the number of pixels within the image. This is achieved by dividing the physical arena measurements with the corresponding number of pixels from the image. Here we calculate the arena dimensions in pixels and then calculate centimeters per pixel of dimension, the automatic suggestion to enter our webcam and cam variable. We should see the robot and the object in the arena and make sure there are no changes in the environment conditions, namely lighting, etc., otherwise we have to do calibration steps again. Once the camera feed has been established, we shall be using robot's calibration data to determine the location of the robot within the image. Ensure that the robot and the object are in different areas in the arena. Now we shall move to get the location and heading of the robot. We shall use the calibration data to determine the location and heading of the robot within the image. For this, first we shall take a snapshot. Then translate the image to the orthogonal view, also called the top view, then determine the coordinates for the center of the colored disk without corrections and the robot's heading or orientation using the rover posses function. We present the schematic that provides an overview of the rover posses function. To obtain the robot's position and heading from the orthogonal image, we have created a function that calculates the robot's position, x, y, and heading. X and y are returned in pixel coordinates. The function is defined as xy heading equals robot posses, imgp, where img is the orthogonal image and p is the RGB threshold values based on calibration data. So the robot posses function does the following things. First, it creates a disk-shaped structuring element, S, which will be used to clean up the image. A structuring element is a key component of morphological operations. It represents a binary-valued neighborhood of pixels, in which the true pixels are included in the morphological computation, and the false pixels are not. Second, after creating the structuring element, it will apply the RGB threshold based on the calibration data in vector p. Third, it will threshold each channel of the image. It will use the disk-shaped structuring element, defined earlier, S, to remove noise from the threshold images. Let's consider that any disk with radius less than 3 pixels is considered noise. Fourth, it will remove RGB points that do not have a radius of 3 pixels. Fifth, it will find the centroids of the 3 colored circles on the marker and use that to determine the center of the disk in the arena. Sixth, it will calculate the heading of the rover based on the red marker that aligns with the forward direction of the rover, using the concept of quadrants. Finally, it will output the heading and xy coordinates in pixels of the robot. The outputs disk center x and disk center y are in pixels. Now that we have the xy coordinates in cm, we shall determine the coordinates of the robot's center while incorporating offset values in centimeters. For this we have defined a function called getLocation, which takes input as the disk center x, disk center y coordinates in pixels, corners, horizontal and vertical offset range from the calibration data, arena height, and the vector containing centimeter per pixel for height and width. The getLocation function does the following steps. First, it determines the horizontal and vertical limits of the arena. Second, it calculates the location offset values. Third, determines the x and y coordinates incorporating the offset values. And finally returns the xy coordinates in centimeters incorporating the location offsets. Similarly, we shall get the location of the object, based on the calibration data. For that we have defined a function called object_pos, which takes input as the orthogonal image and the corners of the arena and the image is calculated from calibration data. The object_pos function does the following things. First, it creates a square morphological object that will be used to clean the processed image later. Second, it stores some constants, namely the minimum x and y along with the width and height, that will be used for cropping the image and computing the target's centroid. Third, it crops the image to focus only on the arena. Fourth, it thresholds the image and removes squares that do not have a width of 8 pixels. Fifth, it gets the object's centroid. Finally, it return the XY coordinates of the object in pixels. Then similarly we shall get the location in centimeters as we did in getting the robot's position in centimeter. Now that we have the location and heading information of the robot and the object, let's visualize the result superimposed on top of the actual image obtained from the webcam. The red dotted line is the baseline and the blue line represents the heading or orientation of the robot, calculated from counterclockwise direction. The image displays the whole scene with the robot, the object, and the arena. Now that we have localized the robot in the arena, it's time to navigate the arena based on the localization results. An overview of the tasks performed has been shown. First, it will use the robot's own location and the object position obtained from localization results. Then it will plan the path to the desired positions. Then navigate to the object location following the path. After reaching the object position, lift the object using the forklift. Then navigate to the final location following the path. Drop the object at the final target position. And the object position from the localization using webcam step as performed earlier. The final position is assigned to the robot by us in the arena. The distance between the points is calculated using the Euclidean distance as mentioned in the equation. The heading of the robot to reach the desired location is calculated as follows. First we have to identify in which quadrant the desired location is in. The concept of quadrant is shown in the image. The quadrant is identified with respect to the robot current orientation. Then the desired heading is calculated using the tan inverse formula as shown. A demonstration of the navigation task has been presented. First we get the location of the robot and the object using the localization algorithm. Here the starting, object and final position have been marked. Next the robot will plan the path to go to the desired position. Now the robot will move to the object position. After reaching the object position, it will lift the object using the forklift and go to the final location. After reaching the final location, it will drop the object. The map of the robot has been shown with starting, object and the final position being marked. The corresponding position error has been shown. As we can that the RMSE error is less than the threshold value of 1.5 cm. Now we shall move to the last exercise, in which we shall perform line following and obstacle avoidance. We have used IR sensor for sensing the path and ultrasonic sensor for obstacle avoidance operation. The path used for this exercise is a white lane with black background as shown. We shall start with two IR sensors to start. This is an open loop control of motor velocities. The overview of the line following algorithm is as follows. When the robot starts, first it will read the data of both IR sensor. Then checking whether both the IR sensors are out of the line. If the answer is yes, the robot moves straight, that is both motor speeds are equal. If the answer is no, then we will check whether the right sensor is on the line. If the answer is yes, the robot will turn right, that is left motor speed is greater than right motor speed. If the answer is no, it implies that the left IR sensor is on the line. So the robot will now move left, that is right motor speed is greater than left motor speed. After this the process continues. Now a demonstration of the mobile robot performing line following under open loop control will be shown. Now as we can see the robot's starting position. The robot will get the data from its two IR sensor and decide how to move forward. As we can see the robot starts moving according to the data it gets from its two IR sensors. Unfortunately, when the robot tries to follow a relatively sharp corner, it fails to follow the path. Possible reasons may be the requirement of more information about the relative position of the robot with respect to the path. The map of the robot has been shown. The failure of the robot has been marked in the map. The starting and the final position along with turns have been marked. The position error for this operation has been shown. Due to relatively sharp turn, we can see that the error suddenly increases and the error crosses the threshold value of RMSE error of 1.5 cm. To overcome this limitation, We shall control the velocities of the motors by PID control. Instead of 2 IR sensors, we shall use 5 IR sensors to get more information about the position of the robot with respect to the path. The general conditions for the robot on white line are as shown. The block diagram for the closed-loop control for the mobile robot has been shown. Based on the heading of the robot, we get the IR sensor configuration which we compare with the desired IR sensor array configuration. Based upon the error signal, PID controller generates a control input which drives the mobile robot. The equation for the error signal and the control input has been shown. A frontal view of the robot has been shown. The overall essence of the algorithm is same with slight modifications. Here we take the input array sensor data and calculate the PID values which are used to determine the motor speeds. A demonstration for such has been shown. Now the rover is placed on the path and its starting position have been marked. Based upon the input from the IR sensor array, the robot will calculate the motor speeds based upon PID values. As we can see that the robot follows the path successfully even on the relatively sharp corner, on which the open loop control had failed. The map of the robot has been shown. As we can see that the robot follows the path successfully even on the relatively sharp corner, in which case the open loop control had failed. The position error for the closed loop control has been shown. The error plot decreases with time and remains steady, thus showing the effectiveness of the PID control as compared to open loop control. A performance comparison plot of open loop and closed loop control has been shown. From this, we can conclude that using closed loop control the mobile robot follows the path without deviating from the original path. Now we shall start with line following with obstacle avoidance. The algorithm flowchart has been shown. The ultrasonic sensor detects the distance of the obstacle in the path. If an obstacle is detected by the ultrasonic sensor, then the robot follows a predefined path when the distance is less than 10 centimeters. After completion of the predefined path, it follows the line as mentioned in the line follower algorithm. If no obstacle is detected, it follows the path according to the line follower algorithm discussed earlier. Now I shall demonstrate line following with obstacle avoidance. The robot is placed on the path with starting point marked. The rover follows as long as the ultrasonic sensor does not sense any object further than 10 cm. As soon as the distance measured by the ultrasonic sensor is less than 10 cm, the robot stops and follows a predefined path. The map of the robot has been shown with starting and final position marked. Position error plot has been shown. As we can see that the position error is well within the threshold error, thus completing the operation successfully. To conclude, we have learned many lessons. We have learned to configure Arduino and wireless communication. Also we have learned differential drive concepts, types of controllers, and analyzed their performance with respect to distance traveled and orientation of the robot. We also learned image processing to help localizing the static objects in real time. We performed line following and obstacle avoidance and analyzed their results. Thank you.